So, have you ever actually watched an owl and wondered, how on earth does it swivel its head almost completely backward without passing out, or, worse, just completely snapping its own neck? I mean, it's an image straight out of a horror movie, right? But for the owl, it is a perfectly engineered, everyday reality.
Welcome to this explainer. Today, we're diving into the 5 mind-blowing owl secrets, anatomy of a silent assassin. We are going to completely demystify the biology and honestly, some of the legendary lore behind nature's ultimate night hunters. We're going to break down the exact real-world science of how these incredible creatures operate.
We've got a super-packed agenda for you today. We're looking at the 270-degree head turn, hearing in 3D, the science of silent flight, stealing animal homes, and finally, a parliament of owls. Let's just jump right into it.
All right, secret number 1, the 270-degree head turn. I absolutely promise you, the biological reality of an owl's neck is way stranger than any myth you've heard. See, unlike us humans, owls don't have spherical eyeballs. They actually have these elongated tubes that are fixed firmly right into their sockets. What that means is they literally cannot move their eyes to look around. They can't roll their eyes at you. So to compensate for this, they've evolved to rotate their entire heads an unbelievable 270 degrees in either direction. Now think about that for a second. If a human attempted to twist even a tiny fraction of that size, the delicate arteries in our necks would just tear. We'd experience severe whiplash, blood clots, or even a fatal stroke because the blood supply to our brain would be entirely cut off.
So how do they survive it? The secret is all in their vascular plumbing. When researchers actually mapped the blood vessels of deceased owls using CT scans and dye, they found something completely astonishing. When a human turns their head, our arteries tend to get smaller and stretch out. But look at the owl. Their arteries, right at the base of the jaw, actually expand. They balloon out into these tiny little reservoirs. So even mid-twist, when they are looking over their own backs, blood is just pooling there, safely waiting to nourish those massive eyes and their brain. It's built-in storage.
And the vascular tricks don't even stop there. The major arteries feeding the brain have to pass through these hollow cavities in the neck vertebrae. Well, in owls, these holes are 10 times bigger than the artery itself. 10 times! That creates these super roomy air pockets that cushion the vessels so it doesn't get pinched. Plus, these arteries enter the neck lower down, at the 12th vertebrae instead of the 14th, which basically gives the blood vessels plenty of extra slack during extreme contortions. Oh, and they have these tiny connecting vessels called anastomoses that make sure the blood keeps flowing no matter what. It's basically a genius fail-safe system.
Okay, moving on to number 2, hearing in 3D and how they literally map out the darkness. So, the crucial thing to understand here is how owls process 2 specific acoustic cues, ITD and ILD. Now, don't let those dense scientific terms intimidate you. Interaural time difference, or ITD, simply tracks the microsecond difference in when a sound hits the left ear versus the right ear. This tells the owl exactly where a sound is on the horizontal plane, left to right. Then you have interaural level difference, or ILD, which tracks the intensity, or basically the loudness of the sound, to map it vertically, up and down.
But here's the really wild part. How do they actually track vertically? Well, several owl species, like the barn owl, possess this extreme facial asymmetry. Their actual ear openings are misaligned. The left ear is positioned higher up on the head and points downward, while the right ear is lower down and points upward. It looks a little crazy close up, but this bizarre physical trait means that a rustling mouse down below the owl will sound louder in the left ear, while a sound coming from above will be louder in the right ear. It is literally built-in surround sound.
Deep within a discrete, specialized region of the owl's midbrain, cells are hard at work processing these unique combinations of time and intensity. Each of these cells responds only to a sound issuing from one specific tiny area in physical space. The result of all this? The owl's brain constructs a highly accurate, three-dimensional neural map of its environment. This allows it to pinpoint and strike its prey in total pitch-black darkness without ever even needing to use its eyes. They are essentially flying blind, but with absolute, perfect accuracy.
Which brings us to number 3, the science of silent flight. Because once they've targeted their prey using that 3D neural map, how do they actually close the distance without making a single sound? The answer lies right in their wing mechanics. Unlike most other birds, nocturnal owls possess 3 very distinct microfeatures on their wings. First off, the leading edge of their primary feathers features these rigid, hook-like serrations. It works kind of like a comb.
Now, as the owl flies, this comb disrupts the airflow, breaking up and completely eliminating the noisy aerodynamic vortex that a normal smooth wing would create. Add to that the soft trailing edge fringes on the back of the wing and a velvety upper surface made of elongated filaments, and you get a perfectly muffled wing stroke. It's acoustic stealth technology perfected by nature.
And this biological marvel is so profoundly effective that it's actually stepped out of the forest and right into the laboratory. Human engineers are currently studying and actively copying owl wing morphology to solve our own real-world problems with noise pollution. Specifically, they're aiming to dampen the roar of heavy traffic and loud industrial machinery.
In fact, scientists have engineered an acoustic aerogel directly inspired by the owl. Traditional soundproofing usually requires these really heavy, bulky layers of material, but by copying the owl, researchers created a super lightweight two-layer material. The bottom porous layer mimics the owl's skin. It contains microscopic cavities that cancel out low-frequency rumbles, like a car engine. Meanwhile, the top layer, which is made of these fluffy silicon nanofibers, mimics the owl's feathers to perfectly dampen high-frequency squeals. It is a total game changer.
All right, on to number 4, stealing other animals' homes. We are about to bust a major, very common myth about bird behavior here. When you picture a bird settling down to lay its eggs, you probably picture a really carefully constructed nest, right? Woven twigs, mud, leaves, all meticulously put together. So where do owls build their intricate nests? The reality is, they don't. At all. Owls are nature's ultimate squatters. They expend absolutely zero energy building their own architectural masterpieces. They vastly prefer to just let other animals do all the hard labor for them. For example, species like the screech owl will simply take over pre-existing tree cavities, or even human-made nest boxes. Burrowing owls take this a whole step further. They literally move underground into the abandoned dens of badgers, prairie dogs, or skunks. And get this, they will even line the entrance of these stolen burrows with dried livestock manure. Why? To mask their scent from predators and to attract tasty insects right to their front door. It's kind of gross, sure, but undeniably genius.
Then you have long-eared owls and those massive great horned owls. They simply adopt old, abandoned stick nests, originally built way up high in the trees by hawks, crows, or ravens. They just move right in, and they do this often as early as January, basically claiming the prime real estate before the original builders even have a chance to migrate back for the spring. First come, first served.
Finally, number 5, a parliament of owls. We've covered their incredible physical adaptations, so now let's explore how human history and mythology have interpreted these downright bizarre biological traits over millennia. You see, long before we had any understanding of CT scans or neural auditory maps, the ancient Greeks observed the owl. They looked at those enormous forward-facing eyes, their absolutely motionless waiting, and their silent, calculated strikes. And they didn't see a terrifying monster in the dark. They saw enlightenment. The owl became the sacred companion to Athena, the goddess of wisdom. To them, the bird symbolized intelligence, deep strategy, and deliberate thought. And this enduring legacy of wisdom is actually what gave us the collective noun for a group of owls, a parliament. Now, the irony here is that most owl species are actually highly solitary and very territorial hunters. They really don't like hanging out together. But when certain species like snowy owls or short-eared owls do occasionally gather to roost together in the harsh winter, sitting completely motionless in the trees, well, they don't look like a chaotic, noisy flock of birds. They look deeply observant. They look exactly like a solemn, ancient assembly, making careful, deliberate decisions. Which leaves us with a really fascinating final thought to ponder. We look at an owl's extreme stillness and we see contemplation. We look at their massive, light-gathering eyes, and we see knowledge. But do we just project our own human ideas of wisdom onto what is, in reality, a perfectly evolved, ruthlessly efficient, silent assassin? I'm going to let you be the judge of that. Thank you so much for joining me for this explainer. Keep questioning the incredible world around you, and I will catch you in the next one.